Here we have a rectangle, and the lengths of both sides have been measured and recorded, and we want to calculate the area. Well, the first step is simple enough. We simply multiply 8.24 by 18.36 and we get 151.2864. Initially, you should keep all these values. However, later on, as we continue to analyze our errors, we will know exactly how many significant figures to retain. So how do we calculate the absolute error in our area? Since we multiplied these values, we can't simply add these. What we need to do is find the relative errors, because the relative errors add up to give us the relative error in our area. So here we have the relative errors in both lengths. So all we need to do now is add these, and that will give us the relative error in the area. So that's what I have here. And now that I have the relative error in the area, I can find the absolute error, because all I need to do now is multiply this by the nominal value. So 0.582% of 151.2864 is going to be 0.8805. So our uncertainty starts in the tenths place. So these numbers then are really not significant, and this should be rounded off to 0.9, which means then that none of these are significant, and this should also be rounded off to the tenths place, in other words 0.3. So as you can see here, we get 0.9. So 151.3 plus or minus 0.9 centimeters squared. Note 0.03 plus 0.04 does not give you 0.9, not by a long shot. We have to add these relative errors here, get the relative error here, then use this relative error to find the absolute error here. So it's going to be 0.582% of 150 of what it was before, 151.2864. That gives us 0.9. Actually, it gives us 0.8805, but this then is rounded off to 0.9. So to summarize, whenever we multiply measured values, the associated relative errors, so we have to calculate them, are added up to give the relative error in the product. Of course, once you have the relative error, you still now have to go and use this relative error to be able to determine the maximum possible error, or the absolute error. Alright, so let's look at division now. Let's say you want to determine the density of aluminum. Well, the first thing you would do is get a sample. So here we have a little nugget, and then you'd get a scale and you'd weigh it. And let's suppose we get this for the mass, 341.873 plus or minus 0.001 grams. Now this picture that I put here is just to brighten up the scene. Obviously the scale doesn't have enough digits over here to measure 341, but you get the picture. Next, we're going to need to measure the volume of this nugget. So we do so by placing some water in this cylinder and measuring the volume. Then next, we place the nugget and we see how much the water rises. So in this way, we could determine the volume, and let's suppose we get 125 centimeters cubed plus or minus 5 centimeters cubed. So now to get the density, we just need to divide the mass by the volume. So that's pretty straightforward, and we get 2.734984. So remember, this is going to be an intermediate value. After we process the errors a bit, we'll know exactly how many significant figures to use. So in this case, we carried out a division. So whenever you divide, you can't simply add up the absolute errors. You have to add up the relative errors, and the result will be the relative error in the density in this case. So notice, even though we're dividing, we're still adding up the relative errors. So we get the relative error in the mass, and it turns out to be 0.0002925%. And then we get the relative error in the volume. So that's 5 divided by 125, we get 4%. So now we add these relative errors, and we get 4.000295%. So now to calculate the absolute error in the density, we simply find 4.000295% of this 2.734984. So we do that here, and we get that the absolute error in the density is plus or minus 0.1094. So the error starts in the tenths place. Note, it will not always be the case that the error starts here. So this could give you 0.005 or 1.3. Whatever you get, well, that's what you get. So this has to be rounded off to the tenths place. So that gives us 2.7 plus or minus 0.1, which is what we have here. So to summarize, whenever we divide measured values, the associated relative errors, and notice in cases like these you have to go and calculate those relative errors, are added up to give you the relative error in the quotient. So now, when you have this relative error, to get the absolute error, you have to use that relative error. For example, if it's expressed as a percent, you have to say, oh, so much percent of this nominal value, and then that gives you the absolute error, or the maximum possible error. So to sum up then what we have discussed here in multiplication and division, we can simply say that whenever we multiply or divide measured values, the associated relative errors are added up to give the relative error in the result. Remember, then you have to use this relative error to then calculate the maximum possible error in the result. So that's it for this video.